Well, good afternoon. Welcome to MOS Live. You're joining us just in time for our coolest science stories, where we'll be sharing some exciting breakthroughs in the world of science. And you'll have a chance to ask some questions about the three stories that we'll share today. Now, if you're joining us on Zoom, you can go ahead and start sharing those questions anytime you'd like by clicking the Q&A button on your screen. If you'd like captions, you can access those by clicking the closed caption button at the bottom of your screen and selecting Show Subtitles. Now, if you're joining us on Facebook or YouTube, unfortunately, we cannot see your questions right now, but we are thrilled that you're tuning in. So let's get started. My name is Megan. My pronouns are she and her, and I'll be sharing a story about quantum physics education. And I am joined by two other fantastic educators from the Museum of Science. So I'd like to invite them now to come on and introduce themselves.
Hi, my name is Meg. My pronouns are she and her, and I'm going to be sharing a story about a new kind of artificial intelligence that needs to sleep, just like us.
All right, and my name is Zoe. My pronouns are she, her, and I am going to be sharing a story about one of the many connections between art and science, which is art restoration. What does that have to do with sheep, like the sheep in my emoji? Well, let's go ahead and find out. Let's get started. Okay, so we are specifically going to be talking about the restoration of a very famous painting called the Ghent altarpiece. Now, this is a very large painting from 1432, which means this painting is almost 600 years old. Now, oil paintings do not last 600 years all on their own. Even after just 100 years, the oil paint will start to crack and peel up from the surface that it's on. And they do cover that oil paint with a clear varnish to protect it from dirt, but the varnish itself can get all yellowed and cloudy. And if it gets really, really bad, you won't even be able to see the painting underneath. So if a painting gets really old and starts to look not so great, how do you restore that painting to its former glory? Well, you can carefully dissolve away that yellowed, cloudy varnish to show the real colors underneath. And you can very carefully touch up and repair any damage that's happened to the paint. Or if you were operating before the 20th century, you'd probably just paint over it. That is something that professional artists were hired to do. Many centuries ago, or even just a couple centuries ago, these artists would go ahead and repaint the image over top of the cloudy varnish so that you could see the painting once again. However, this led to some interesting situations because some of those artists would take this chance to go ahead and fix things that they thought were wrong with the original painting. So that leads us to the science story that we have today. There was a paper published just a few weeks ago talking about some of the science and the techniques that went into restoring the mystic lamb of the Ghent altarpiece. And the mystic lamb is that kind of small but central character down in that lower panel. Now, for a long time, at least 50 years, people have thought that maybe the mystic lamb had been overpainted at some point. Why did we think this? Well, in the 1950s, when people were doing some restoration work, they decided to remove some extra layers of paint that were around the lamb's head. So you can see in this old photo from before the 50s that the lamb does have 2 ears. That's probably what you would expect from a lamb. However, after they removed that paint, they wound up with a 4-eared lamb. And if it's a little hard to see those ears, here's an outline. So that shows that the original ears from the lamb were covered up by a different artist. Okay, well, in that case, maybe the rest of the face was also covered. How can we tell? Well, let's go ahead and look at some of the science that they used here. They used a technique called spectroscopy. Now, spectroscopy is a really useful technique. You can use it for all sorts of things, but essentially what you do is you take light and you shine it on a small sample of stuff. All right, then you look at what kind of light gets reflected or maybe even emitted as a result. And looking at that light can tell you what your small sample is made out of. Pretty cool stuff. Now, the thing is, if you're looking at a whole painting, it's not enough to just check out one small sample. Instead, you need to look at something, kind of a pretty new technique actually, called imaging spectroscopy, where you look at many, many, many small samples. Now, let's say that these small samples are mapping out the locations of molecules A, B, and C. If you take all that information and map it out, then you can wind up with kind of an image that shows you where the different molecules are on your painting. And that is really, really useful information for art restorers. Okay, now let's go ahead and look at the techniques that were used in this particular paper. They were using macro X-ray fluorescence and infrared reflectance imaging spectroscopy. Kind of a mouthful, but the former one, which is actually being shown in the picture here, that can show you the locations of actual elements like gold or lead or mercury. And the latter can actually show you original sketches underneath the paint, because that's one of the really great things about these techniques. They don't just show you what's on the surface, they show you what exists, what molecules there are in all of the different layers of paint. Very useful stuff. Okay, so what does this data look like? Well, it can look something like this. And that's a lot to interpret. There's a lot of things going on. So maybe we can focus on just a couple of these images to show us some clues about what the lamb's original face might have looked like. All right. First of all, let's look at some of that X-ray data, specifically for mercury. Now, mercury was in the red paint on this painting. And if we go ahead and put some arrows up, we can see that red paint was used in the nostrils. But there's actually two sets of nostrils that are present on this painting. Only one of the sets of nostrils is visible, the lower one. The upper one has been covered up. So maybe the lamb's original nose was actually higher up, and then some other artist came in and painted it lower. All right, well, looks like the ears were overpainted and the nose was overpainted. What about the eyes? If we go ahead and look at that infrared data, we can see those sketches that underlie all the paint. And if we go ahead and pull up those arrows again, we can see that the original eyes were supposed to be much larger and more centered. That is how the original artists envisioned those eyes. Clearly, they were covered up later on with eyes more to the side. Okay, so this is really good evidence for the art restorers to figure out that there is in fact overpaint and it's covering up something pretty significant. That's the kind of evidence they need to decide that they should scrape away the overpaint. And they did indeed decide to scrape that away just a few months ago. What did they find underneath? Well, it turns out the original face of the mystic lamb looks like this. Now, this original face has been called by some alarmingly humanoid. You might have your own opinions on which face you think was better. Personally, I am a big fan of this one, but all of that aside, I do think the most important part and the most interesting part for us today is to think about that science that goes into being able to see the different layers of paint before you can even scrape them away. That is really cool stuff and extremely useful for all of those art restorers. All right, so with that, let's go ahead and pass this off to our next presenter to hear a bit about quantum physics.
Great, thank you, Zoe. That was such a cool story. I love that we can use science to help us preserve all of this ancient art. Really cool. All right, so now we're gonna switch gears and move on to a little bit about quantum physics. So, as September approaches, one thing that's on a lot of people's minds is the start of the new school year. And even though school will be a lot different for a lot of students, the curriculum should be pretty much the same, right? There'll be math and history, biology, and what about quantum physics? Now, quantum physics is the study of the tiniest building blocks in our universe, like atoms and subatomic particles, and it's usually not something you learn much about until you get to college. But that might be changing. This month, the National Science Foundation announced the National Q12 Education Partnership, This new program is joining forces with the US government and other institutions to introduce quantum science and technology into kindergarten through high school education. The goal is to prepare students to become part of the future quantum workforce. But what is a quantum workforce and why do we need one? Well, let's find out. Now, quantum physics is often portrayed as a lot of complex equations on chalkboards, but the theories of quantum physics are more than just a lot of math. All that math tells us that quantum particles, like the electrons in an atom and particles of light called photons, can do some pretty amazing and unexpected things. Like they can be in two places or states at the same time, something called superposition. Now, let's say these two quantum particles can be in two states that we'll represent as green and purple. If a quantum particle was in a superposition of these two states, well, that means that it's green and purple at the same time. Not a blend of the two, it's all the way green and all the way purple, all at once. Now, things on the human scale don't behave in this strange way. If they did, well, this cat could be standing up and lying down at the same time. And there's more. Quantum particles can also have a powerful connection between them called entanglement that allows them to affect each other. Now, let's assume that these two particles are entangled, and one is purple and the other is green. Now, if we change one to green, the other automatically instantaneously changes to purple. They're connected. And this will happen even if you separate the two particles across the whole universe. Now, there's a lot more cool stuff to learn about quantum physics, but aside from it just being fascinating, there's another important reason to learn about quantum physics. It could be a huge part of the future of our technology. Scientists are now harnessing the cool properties of the quantum world, like superposition and entanglement, to create powerful new quantum technologies. Things like quantum computers. By harnessing properties of atoms and particles, these powerful new machines could solve certain types of problems that are way too hard for even the most powerful computers that exist today. Though quantum computers would be really good at things like climate modeling and discovering new medicines. And scientists are also building new quantum communication systems that could keep our information safe from hackers. By encoding information into photons of light and entangling them together, scientists can create a quantum key, like a secret code that's nearly impossible to break, allowing us to send information securely. Imagine never needing to worry about hackers stealing your credit card information if you buy something online. And China's been leading the way on quantum information, using satellites to teleport information from Earth to outer space. In the future, this and other methods of quantum communication could be used to send information securely between quantum computers around the world, creating a new quantum internet. But in order to make things like quantum computing and the quantum internet a reality, we need more scientists and engineers who can create, build, and maintain this technology. We need a quantum workforce. By learning the basics of this science early on, students who are interested in pursuing careers in quantum science and technology will be ready to dive into the details when the time comes, perhaps when they get to college. And even if you don't work in the field of quantum science, well, we all need to understand what this new technology is and how it might affect our lives. And that's the goal of the National Q12 Education Partnership. Over the next decade, this partnership will establish lessons and resources for students of all ages that will make quantum science and technology education accessible to everyone, so that people, no matter who you are, can understand and appreciate this exciting and fascinating field of science. So keep your eye out for more quantum science as it expands into our schools, museums, and other educational institutions. Now, if you're interested in hearing more, or if you have questions about quantum science and technology, join us for MOS Live Ask a Scientist on Monday, August 24th at 3 p.m. And you'll have a chance to hear from some scientists who are working in the field of quantum technology right now. So check out our website or follow us on social media for details. And you can also start posting your questions about any of the stories that we have today at any time if you're joining us on Zoom. So get those questions coming in, and we're looking forward to answering as many of those as we can at the end of the show. And with that, I'm going to turn it over to Meg, who has our final story about artificial intelligence.
Hi, yes. Thanks for that wonderful story. It's so exciting that those really important concepts are going to start being part of the curriculum at such a young age, so that by the time those youngsters become part of the quantum workforce, they're ready to go. But first, I'm going to change gears a little and ask you, have you ever stayed up too late? And how did that make you feel? What if you got some sleep afterward? What about then? Do you think that your computer would feel that good if it got some sleep too? Well, a new study from the Los Alamos National Lab shows that some kinds of artificial intelligence, or AI, might benefit from sleep just like we do. To understand how that might work, let's take a look at how sleep works for us. So your brain is an electrochemical organ. That means that the brain cells, or neurons that make up your brain, send signals to each other via tiny electric impulses, or brain waves. These brain waves fire faster or slower depending on what you're doing. They're pretty fast, for example, high frequency when you're awake and doing something that engages you, like watching a really neat science video. But when you start to fall asleep, your brainwaves start to slow down, going through several stages until you reach deep sleep, or slow wave sleep, where the brainwaves are slower and more even. Over the course of a night, you actually cycle through these different sleep stages, going from slow wave sleep back up to lighter sleep, where you might experience dreaming, and all the way back down. Scientists are still working to understand exactly what slow wave sleep does for us, but it seems to be involved in refreshing and repairing brain cells and other systems of the body that have been working hard all day. That's why you feel so much better after you get a good night's rest. Now, a team of researchers thinks that similar benefits of sleep might help keep artificial intelligence programs running smoothly too. They're using a special type of program called a spiking neural network to try and approximate how humans perceive and recognize images. So neural networks in general are computer algorithms that are really good at recognizing patterns, like interpreting this handwritten number 7 correctly. They're built to mimic how our brains do this task, in fact. A spiking neural network is a special type that goes one step further, mimicking how the brain's neurons fire in bursts rather than all the time. This is really hard to do, but the payoff is huge in terms of power efficiency. Just think of all the amazing things your brain can do, and it only runs on about 20 watts of power, which is less power than it takes to run a laptop computer. The research team gave their program a particular task called unsupervised dictionary learning, which is a fancy way of saying they gave it some images to look at and they asked it to come up with a dictionary of visual elements, the words in the dictionary, to describe them. By using this kind of training for their neural network, they were hoping to recreate how humans learn from their environment during childhood just by taking in their surroundings. It's a little like handing you a cookie and asking you to figure out the recipe just by eating it. You could probably come up with some good ideas about what's in there all on your own, that is unsupervised. That's what this team of researchers did with their spiking neural network, but with images instead of cookies. They gave their AI many images, and these are all from a well-known data set of tiny pictures, each just 32 pixels on a side. So you can see here a sort of blurry car. The middle one is a frog if you squint, and there's a blurry truck at the bottom. But it actually doesn't matter what's in the images, because all they needed for this kind of training, all they're interested in, is whether their program can reproduce what's in the images. So left to its own devices to learn a dictionary of visual words or patterns, it came up with something like this. This might look a little strange, but the important thing to notice is how all of these different squares are so different from one another. They have different patterns and colors so that between all of them, they make up a whole vocabulary to describe lots of different images. Then from combinations of these strange looking words or patterns, the team asked their AI to recreate the original images. Imagine if we asked you to bake some cookies just based on what you learned from eating them. You might get pretty close. And so did they. It seems like the AI really did learn the most important visual elements to describe these images to a pretty good extent. But they ran into an unexpected problem along the way. During these unsupervised learning periods, the spiking neural network started to become unstable, meaning that the nodes in the network would get carried away and start spiking in response to noise. They'd just be firing all the time, completely messing up the simulation. Here's what their dictionary started to look like over time. So at first, it's going through the images bit by bit, and some reasonable looking patterns or words start to show up. They have different patterns. That looks promising. But then as it keeps learning, the nodes just start spiking all the time, and the words start to look all the same. They become completely meaningless. The researchers struggled to figure out what was going wrong until they tried something a little unusual. They broke up the unsupervised learning periods and spaced them out with naps. In between short bursts of learning from the actual images, they started showing the AI fake images that were just noise, and they changed the noise over time in this wave-like pattern. When they set the AI to learn its dictionary this time, it behaved very differently. Instead of the spikes growing continuously over time, they calmed down. And after some learning, they started to see reasonable patterns, more words showing up in their dictionary. And after even more learning, these patterns got more distinct and well-defined, which is what you'd want. These little slow wave naps calmed down the spiking neurons and kept them from hallucinating. That's what led the research team to compare this technique to giving their AI a well-deserved rest. So this sleep-inspired technique is likely to be useful for all sorts of future AI applications that want to use these spiking neural networks. And the team's next goal is to try it out on a neuromorphic chip that's hardware specifically designed for these types of programs. The team also wonders what this research might tell us about our own brains, and they speculate that maybe one reason slow wave sleep may have evolved in us is to keep our own neurons on task. And with that, I'm going to invite my fellow panelists to join me back on screen, and we're going to get to the Q&A portion of our show. And if you have any questions for any of the three of us, please type them into the Q&A box on Zoom, and we'll be really excited to answer those. But just to start things off, I have a question for Zoe about the art restoration techniques that she was talking about. What kinds of light were they using in order to investigate that painting?
Yeah, so when we think about light, we usually just think about the light we can see, which is called visible light. But that's actually only a very small part of what we call the electromagnetic spectrum, all the different types of light that can exist. So that actually includes things like microwaves and even X-rays. All of those things are types of light. Now, what the people in this particular study were using was infrared light, which is just a little bit lower in energy than the light we see, and X-rays, which are much higher in energy. And it was actually really useful for them to use these two techniques together because it turns out they kind of cover each other's weak spots. There's some things that infrared can't identify very well that the X-rays can. There's some things that X-rays can't really deal with that the infrared can. So it's one of those really cool things that you can figure out how to use different science techniques together to get the best results. All right, now it looks like we've got a question here from Clement, age 9, for that lovely story about sleep and AIs. So why do we need to sleep?
Yeah, that is a great question. So there's a whole field of study dedicated to sleep research. So it's definitely something that scientists are still working to understand. There's a lot of things we don't know about what sleep does for us, but we do know some things. And it seems that those periods of deep sleep or slow wave sleep are especially important for sort of refreshing a lot of the body's systems. So we know that the brain cells themselves are consuming more glucose during those periods. So maybe they're getting a little refresher. And it's also the time when human growth hormone is secreted, which is being sent all around the body to different systems that need to be repaired, basically, or to need to grow while we're sleeping. So we know that there are some concrete, definite benefits to sleep, but we are still working to understand exactly how it all works, which is why it's very interesting to see an application in artificial intelligence. This research group speculates that maybe their research could tell us something about our own brains, which if some brain scientists picked it up and started to look into that, maybe they would be able to lead to another insight. So these two fields being so different can really sometimes tell us things about each other. Okay, there's a whole bunch. Okay, let's see. I'm going to ask Megan a question. So if these effects, these quantum effects only matter for very, very small particles, why are they so important?
That is a super good question. And I think the reason they're so important is that even though they happen on this really, really small scale, like the scale of atoms and tiny particles, really we're all made up of those atoms and particles. All the stuff that we see, matter everywhere, is at its most fundamental level made of quantum things. So even though we can't see those effects, on the human level, they're kind of blurred out because they happen on such a small scale. They are important because it's sort of the science that is the foundation of everything around us. But they're also important, and the big reason why quantum physics is being pulled into education at younger ages is that it's kind of bringing about this revolution in technology where we're going to see things like quantum computers, and even now things like quantum communication are starting to be established and used right now. And so it's really important for people to understand why those things are happening and how they're happening. And I mean, it's just fascinating. Yeah. So I have another question for Zoe. And I'm curious, now it sounds like they were actually able to restore this painting and they were able to reveal the original lamb by scraping off the paint. Do you know anything about how they did that? Because that seems like it'd be really hard to do.
Yeah. So one of the things that helps them is that I talked about how there's a layer of varnish over top of the oil paint. Well, if someone comes in and overpaints, then all of that paint is going to be on top of the varnish with another layer of varnish on top of it. So you'll get these layers that build up. So that helps them figure out what they should scrape away and what they shouldn't scrape away. That helps them figure out when to stop. But the actual scraping occurs with scalpels, like really tiny little razor blades. And they pull up a microscope to help them get a really close look, and then they slowly scrape it away. So yeah, they really are physically removing that paint, which means you have to be super sure that you want to remove the paint, which is where all of those science techniques come in. They really help the art restorers make those decisions in an informed way.
Wow, that is so cool and amazing that they're able to do that. Well, it looks like we are just about out of time. Thank you so much for all of your awesome questions. I'm sorry that we didn't quite get to all of them, but now I'm going to give my fellow educators a chance to say goodbye before we close out.
Thanks, everybody. Bye.
All right, thanks so much. Well, there is so much more going on over at MOS Live. So, sorry, I had a sharing mishap. Well, there's a lot more going on over at MOS Live. So Please check us out on social media or check out the website mos.org/MOS at home to see what we're up to. If you enjoyed this program and you're interested in supporting the Museum of Science and our continuing online program that we're continuing to make accessible to everyone and free of cost, you can check us out at engage.mos.org/welcome to support Moss at Home. All right, thank you so much, and thank you for your questions. We had so much fun with you today, and we'll see you next time.